Hey, everybody. I wanted to do a quick review of the tangent plane so that we can remember what the formula for it is, and maybe more importantly, remember where it comes from so we can recognize it and understand what it's telling us. So let's just do it quickly. This is a review. I'm not going to go into as much detail as I might have introducing it. So I've started here with a function of two variables, z equals f of x, y, and I've sketched a surface here. I'm not drawing axes in, right? This just is somewhere in our three-dimensional coordinate system, and I've put a point in there where we're going to create our tangent plane. So I'm going to give this point a name. I'll call it P, and let's say P is the point x naught. This is a little thick. Let's do this. P is just going to be x naught, y naught, z naught. That's better. X naught, y naught, z naught. And we want to create the tangent plane there, okay? So we're working a bit intuitively here. Everything I say can be shown rigorously or defined rigorously, but it should match our intuition with what we want a tangent plane to be. And the way we get it is we start with two vectors, okay? And these vectors are what's going to define a plane, right? Imagine any two vectors you put together, however you have them oriented, as long as they're not parallel to each other, you can imagine the plane that they define, right? There's a surface that contains them, a flat surface. So the two vectors we're going to choose are going to be the vectors given to us by, we're going to use our derivatives, our partial derivatives, to help us understand these vectors. So let's start with the partial derivatives, and then I'll make some intuitions about the vectors that come from them. So let's look at the vectors f of x, sorry, not f of x, our first partial with respect to x at this point. And we're going to look at the first partial with respect to y at this point, okay? These are not vectors, these are numbers. I think I might have just misspoke, but I'm going to use these to get some vectors. So let's think about f, this x derivative. The way to think about this is, if we hold y constant, then we're looking at a thin curve along this surface. So for instance, this might be tracing out a line where y is constant, right? So it's supposed to be going over that hill there. So, right, in this, the way I've oriented, y would be going in this direction, and x is going in the direction of that line. So I'm only changing x as I move along the surface, keeping y constant, okay? And this derivative, what it tells me is, I don't want to make this drawing too complicated, but if you can imagine a sheet of paper slicing through the surface so that it cuts right where I've drawn that line, that can be considered a plane. And this line I've drawn is a function in that plane. And this derivative, this partial derivative, would tell me the slope of the tangent line within that plane in the x direction, okay? So what does this number mean? If I take a partial derivative and evaluate it at this point, f, right, the slope of a tangent line tells me that, actually, let's do it in terms of a tangent line. If I just think of y equals mx plus b, what does this mean, this slope m? It means if I change x by +1, y changes by m, right? If m is positive, y goes up. If m is negative, y goes down. Well, now this is telling me how z changes as x changes, okay? So this number is telling me if I change x by positive 1 and hold y constant, z changes by this number. Okay, so that's a way to think about the slope of this tangent line right here, right? We're fixed in this plane. If I'm fixing a value of y, the plane y equals y naught, in fact, is the plane that we would be slicing through here. If I live just in that plane and think about this curve traced through the surface, at this point P, if I change x by a positive 1, and I'm moving along this surface, then at that point, I'm moving at a rate as if z is changing by the value of the partial derivative there, okay? Let's translate that into a vector notion. So I'm gonna draw a vector right here now. I want it to be along this tangent line, okay? Well, that vector, let's call it, I'll just call it x. No, that's not a great name for it. Let's just call it u. I don't want to get too many x things going around. U, what is u? What has to be true about the u vector? Well, the u vector has to have it so that if I change x by 1, z will change by the amount of that partial derivative at that point, okay? And y isn't changing. Nothing happens to the y coordinate along that vector, okay? So there's the first vector I want. The second vector, I won't go through the same process, but it's really the same thing just in terms of y. I can play this same game. I can imagine fixing x, meaning x doesn't change, and tracing out a line along this curve, or this surface, excuse me, somewhere back there it goes out, right? So you can imagine if you want to think about walking up a hill, this is like if x is north and y is east. The first time we were walking along this hill, only traveling north, not changing directions east and west. As we got to this point P, it's like every step forward, we had to go up by the value of the partial derivative. Now we've gone back down to the hill on this west side and we're traveling perfectly east in the y direction. And as we get to that point P, we are now climbing that hill. Our z is changing for each 1 unit of y value we gain. In other words, in each 1 unit of easterly value we gain at this point, we gain the y partial derivative at that point in z value. And so there's a vector I want to draw here, right? So it's a little hard to see. It's if you drop this down, it's going to be right above, like its shadow from a light above is on that line. Okay, it's hard to draw this. Let's call that v. This one has the same idea, except x isn't moving. If we change y by 1, z changes by the value of the y partial derivative at that point, okay? And so now we've got these 2 vectors, and I want to imagine the plane that contains them, right? So you can imagine them both sitting. So this plane would be just sitting, touching that point. That tangent line I talked about in the x direction would live in this plane, right? There's this line right there. We could do another one in the y direction, like this, and that plane would contain them. So what plane is this? Well, what do we need for a plane? We need a point and we need a normal vector. We already have the point. We know we want to be at the point P. What we need is the normal vector. And to get the normal vector, I need 2 vectors in the plane. I can take their cross product, right? This is one way that we can get the normal vector. And I've got these 2 I've got these two vectors in the plane, okay? So if I take their cross product, I'm gonna get, let's see, negative f of x. Sorry, I keep saying f of x. The partial with respect to x at x naught, y naught. The second component is gonna be negative of the partial with respect to y at the same point. And the last one is just 1, okay? If you did v cross u, the negatives would switch. We'd have a -1 and positives there, but it won't change what's going to happen in the end. Sorry. Okay, so this is what I'm going to use as the normal vector for my plane. So now I just write the equation for a plane with this normal vector through the point P. And that equation looks like this. We know n dotted with this vector here is going to be 0. So let's take a moment to remind ourselves what this equation is saying. I'm going to get rid of our surface now. Just look at our plane. See if I can do this without screwing up. Just keep those vectors. All right, I'm starting to push my luck a little bit here, I think. Okay, so now I've got this plane with, actually, I don't need those two vectors anymore, that's right. So now what I'm left with, I've got a normal vector here. Whoops. I've got a normal vector here. This is the vector I just computed, perpendicular to those two vectors I just erased. And this point P. All this equation is saying is, right, x naught, y naught, z naught is this point right here, that's point P. If I take any point in the plane, right, so x, y, and z are variables, x naught, y naught, z naught is a specific point, so those three components are numbers. If I take any point in the plane, this vector here is what I've drawn over here, right? So to any arbitrary point, this is a vector starting at point P and pointing at that, and this equation just says those vectors all have to be perpendicular to n. So there's the definition of our plane right there, okay? So let's finish this up. We're almost there. Now I just take this dot product. So I've got n written right up here, so I just need to multiply each of these components by each of these components here and add them together. So I get, it's going to get a little bit ugly for a second, negative this x derivative times x minus x naught minus this y derivative, y minus y naught. Oops, sorry, I skipped the evaluation of that derivative. So this is at the point x naught, y naught, then times y minus y naught. And then I get plus z minus z naught equals 0. Just to clean things up a little bit, I'm going to add everything over to the right-hand side that's negative. Except I'm going to leave the z minus z naught on the left. And so we get this form. Z minus z naught is equal to, now this is positive because I've added it over. And I get this nice formula for the tangent plane, right? And there it is. So let's look at the pieces really quick. I just want to point out this whole thing and this whole thing, those are just numbers. Each of them is one number. So there's a constant in front of this x minus x naught and a constant in front of this y minus y naught. Also z naught, x naught, and y naught are also numbers, okay? So, right, this would look something like, well, I'm just gonna make up some numbers. If we had, it might look something like right? Anything like this, whatever those numbers are, right? I just want to be clear what this is going to look like in the end, okay? One other thing we might do, let's copy this. It's also sometimes convenient and useful it's red, to just take this equation and add that z naught to the other side. Right, so if I add z naught to the other side, I'll get z equals that same thing with this z naught now on the other side. What is this saying? This is like, so let's think about, remember z is our function. This is the output of the function. Z naught is the output of the function at the point we care about, at this point P, right? Here's our output. Okay. This is a change in X. This is a change in Y, right? If I change, so right, I've got X naught and Y naught, remember our numbers, at the point we built this thing at, this tangent plane at. If I put in values for X and Y, how far away they are from X naught and Y naught is what this X minus X naught and Y minus Y naught give us. They give us how much we're changing from that point. Well, we take the change in X and multiply it by the derivative with respect to X at that point. So we're saying how much does Z change if I change X, and multiplying that by the change in X. That tells us how much Z is changing at that point based on how much we change X. And then we do the same thing for Y, and we add those two changes together and add them to where we started. That tells us how much total, where we'll end up with after we change in the X and Y direction. Of course, it's a tangent plane, it's not the surface. And so on the surface, once we leave that point, how much we change Z starts changing itself, but it gives us our approximation, right? If at that point, changing X by 1 changes Z by 10, and changing Y by 1 changes Z by 1,000, if we change X by 1 and Y by 1, we expect to change by about 1,000 plus, what did I say, 100 or 10? I can't remember what I said. Whatever the sum of those two numbers, 1,010, I think I said. And then if we add that to where we started, we get an approximation for where we'll end up. And that's the whole idea behind the tangent plane. And this, the last thing I've written, sometimes people write with some other notation like maybe L of xy, the linear approximation to our function. It's just the tangent plane, but adding that z minus z naught to the other side, okay? Okay, that's it. Thanks, everybody. I will see you next time.